and Shubham, so I'll try and make a go of that. Um, so I'm going to spend the next about 6 to 8 minutes just sharing with you where are we heading on the non-radiological aspects of looking at potential for screening. Where do we stand on the molecular landscape? We know that molecular characterization of tumors is increasingly being used in treatment decision making. The molecular analyses these are typically acquired on tissues currently as we speak, but the tumors are heterogeneous as we know. Sampling in its entirety sometimes can be a challenge, and more importantly, some of these tumors evolve over a period of time. When we're looking at environment within the structure, and where are we heading with regards to some of the potential options for blood-based analytics in that space. Effectively, as we've seen, there are various subsets of biomarkers which are currently in play today, and they range across the entire spectrum of oncology. Some of them are still within the research structure, some of them more in advanced stages, some are clinically being applied in various subsets, and they range between looking at various fragments of either tumor cells to circulating tumor DNA to various aspects of transcriptome analysis within the structure. We know that metastatic disease is responsible for a vast majority of deaths. And the Australian pathologist Ashworth told us over 150 years ago that the circulating tumor cells were fundamental as a prerequisite for the metastasis within that perspective. We've increasingly also seen a large amount of activity and data looking at circulating tumor DNA as a real-time tumor dynamic marker, allowing the evolution of tumor changes that can be monitored over a period of time. And the fact that the circulating tumor DNA is exquisitively specific for the individual's tumor, because by definition, those somatic mutations are identified by their presence in the tumor DNA, and they're absent in matched normal DNA. I have any confusing falsehoods with regards to where is that coming from. Effectively, when we've looked at circulating tumor cells, again, the challenge largely within the perspective of looking at the landscape of circulating tumor cells has really been related to adequacy of isolation. We know that there are certain stem cells that are very special type of cell populations within the tumors. They're largely self-renewal, sometimes unlimited proliferation, indirect differentiation within that process. And these circulating tumor cells possess the stem cell properties within the perspective and represent a critical population that can predict tumor progression. Increasingly, we've started to see the use of tumor cells within the perspective of flexible downstream molecular analysis. And I think that's what the future really holds for the science. And we will see much, much more in terms of expression and other aspects of analyses within the perspective. Just to share a little bit in terms of where we are on the circulating tumor cell, and I wanted to go into a bit of the details of the EMT, which we're, I think, all aware of, but one of the important aspects of the change of the epithelial markers from the circulating tumor cells and the property that they use to invade the blood and the lymph capillaries as they swim down freely onto other aspects, it's important to understand that not all circulating tumor cells will undergo EMT. Some of them will undergo only a partial change, and some circulating tumor cells may actually undergo a mesenchymal to epithelial transition at a later stage. And then this leads to a very perplexed environment and a situation where there's a lot of diversity within this population. And when we're looking at largely a downstreaming or a downregulation of E-cadherin as part of the EMT, a large number of technologies that use today detection for some of these nuclear fragments, some of these tumor cells, and if we're looking at capture of circulating tumor cells through a defined epithelial protein expression, and if we've got a heterogeneous population within the perspective, it's almost as looking at a needle in a haystack within the scenario, which is almost an impossible task. The various studies, so I'm not going to spend too much time in terms of detail in some of those, but I think it's important to understand that various studies, including the Louisiana State University study a couple of years back, which was a 3-year experience, did demonstrate that there is ability to look at inadequacy of lung cancer tissue sampling, and that still remains a challenge with one of those perspectives, and obviously tumor heterogeneity remains another one in that space. It's really down to the tumor microenvironment microenvironment. And I think this is really which is going to hold the potential in the coming years for us to look at various biomarkers, which look at diagnostics or screenings within the perspective. I think the biomarkers that are being generated either from cancer cells or from the tumor microenvironment or from the host response to the cancer, and then various molecular factors that are being implicated in lung cancer carcinogenesis that are being evaluated from a diagnostic and other perspective, and even looking at epigenetic markers like DNA methylation, looking at microRNA, and a lot of these studies have been done. I'm going to share a few of them with you. So one of the earlier studies that came about 7 years ago was the one by JET, which was really looking at the early CDT test. This was largely a test which is still commercially available today based upon ELISA, which was looking at a group of about 7 tumor-associated antibodies. And later on, various studies have also been done to evaluate the role of looking at microRNA and that potential that the microRNA can hold within this perspective. Earlier this year, we saw the methylation signatures of cell-free DNA. This was the study that came across in the annals, which we're all aware of, which looked at over 50 cancer subtypes, which had in excess of 6,000 participants in that perspective. And the authors came back to suggest that the data profiling had compelling evidence to look at methylation, which can detect and localize a wide range of non-metastatic and metastatic cancer types within the structure. Unfortunately, the we had with this data was that in the early on subtypes, which we're really looking at for in the 18 to the 35 into the 39% study was not increasingly, a lot of activity has started to take place of looking at various subsets of clusters. Again, they're not new, but this was data that came last year, which was looking at detecting various aspects of cancer clusters across populations of different cancer subtypes. And in this, over 5,000 patients were evaluated, and over about an 89% ability to capture clusters was determined as part of this process. One of the reasons why this approach was slightly different was because it was looking at not traditionally looking at the positive or the negative enrichment within the perspective, but really looking at the way the cells use apoptosis as a resistance mechanisms to survive, and how you could look at direct tumor and other aspects of those processes to identify some of these tumor clusters. So if you're able to see this video, I'm just going to show you over the next about 8 to 10 seconds how these clusters generally evolve. So within this process, what's happening is that peripheral mononuclear cells obtained from blood cells are being taken. They've been transferred to wellplate and in an epigenetically active media. And you're seeing at the end of the day, all those apoptotic resistant clusters are able to survive this mechanism, and you can use these clusters for staining. This was just the study which has just come out. This is one of our studies. This has just come out this week in AACR in cancer prevention, where we've now started to follow these clusters in asymptomatic individuals. And we had about a 3.6% population which had access to the clusters of what we were looking at within the space. And it's important to understand these clusters are unlikely to be influenced by ethnicity. I think that's very important, because in the current strategy, what it offers, if there's a high sensitivity and specificity that can be achieved in those structures, then they hold enormous potential in that space. Whenever we talk about anything related to the aspect of screening, it's always important to know what's going to be our sensitivities and specificities within the system. If the test is too sensitive but less specific, it's going to lead to false positives, and it's going to create various aspects of source uncertainty and issues related to adequacy in terms of follow-up. Further aspects which confuse the matter, not for today's talk, but for other aspects, is looking at clonal hematopoiesis of indeterminate potential, which has a challenge in this space. So we really need to understand, if we're looking at a diagnostic for screening, what's its individual performance, what's its performance when we're applying it in conjunction with a standard that's being used today, let's say, for example, the LDCT for lung cancer. And then ultimately, the more important point and the answer that we need to look at is what's going to be the impact of looking at improving mortality and all-cause mortality within those perspectives. I think we are learning more and more about genomics as time moves on. It's not a perfect world today, but I think it's less imperfect than what it used to be before. And we do need standardization and reproducibility when we're looking at some of these data points to come across. And whether it's a question of looking at various fragments, whether it's the cell or whether it's the cell DNA, those aspects always take importance with regards to the structure. Had we been on a real conference, I would have given you some take-home points, but because we're all in our offices or homes, so I'm going to give you some stay-home points where you stay home and stay safe. So my conclusions, there's an offer of potential, I think, from genomics in terms of where we are. Lung cancer has high prevalence, high morbidity, high mortality. And the main rationale for looking at screening is, can we look at earlier detection, obviously, and can we use earlier detection to have a better outcome in that space? When we look at various standards of tests to be involved within the space, we're never going to get a gold standard that's going to look at 100% sensitivity and specificity. That's not going to happen. But I think Versi made a very, very valuable comment, I think about 8-9 years ago, when he came back and said, you know, as science increases its hold on medicine and clinical medicine and also on diagnostics, there is going to come a time when we're going to have tests and solutions within the space which are probably going to be the best available as they are currently today, and they'll serve as a gold standard against which new tests can be compared. And when those new tests come in and are much better, they'll make the existing tests untenable within the space, and that's where it's going to end. I think cancer represents a complexity of a problem, as does genomics in terms of our understanding of the space. And as our understanding of tumor biology increases within the space, I think we'll have many, many more technologies which can help us elucidate some of those approaches. So I think the approach has to be integrative. You can't displace one technology with the other. You've got to manage and see how can you use both of them more effectively to get a better outcome. So I've tried my best to try and close that within that period of time. So thank you very much for the opportunity.